Hi everyone, welcome to another edition of the AnandTech podcast. I'm your host Ian Cuttriss, and joining me today is our editor-in-chief Ryan Smith.
Hey everyone.
Today's podcast, we ended up focusing a lot on AMD just because that happens to be what's been in our inbox for the past couple of weeks. It's been a long and stressful weeks dealing with the new Ryzen 2000 series CPUs, AMD's new take, using GlobalFoundries 12nm process. We're going to speak a little bit about our research into timers, into system-based timers and the effect on performance that we've observed. And we also got time to talk about some interesting things regarding Kaby Lake G. This is Intel's Core with Radeon RX Vega chip that is now out in the open and being tested. Ganesh has his review of that, but we have some news regarding the chip, and Ryan's going to take us through a bit of that. And then, if we've got time, we'd like to speak about the new hires that Intel have been doing recently, or at least have announced recently, because they've been picking up some very important people around the industry. I know it's been something you've been tracking, Ryan.
Oh yeah, of course. A lot of people in this industry, and I always feel sort of essentially only focus on the rock stars, but, well, the rock stars are rock stars for a reason, so where they end up tends to say a lot about what a company is planning for future projects and what kind of reason they need.
So, first topic on our podcast today is going to be the Ryzen 2000 series, or Ryzen 2nd Gen, or Ryzen 2, however you want to call them. This is the second generation of Ryzen product. We have 4 CPUs to choose from that AMD have released, 2 Ryzen 7s and 2 Ryzen 5s. Now, this is 2018. We are dealing with Ryzen 2, which is technically Zen Plus. So the original Ryzen 1000 series used the Zen microarchitecture. We're expecting AMD to launch Zen 2 sometime next year, according to their roadmaps. So in the interim, we've got what's called Zen Plus. This is essentially the same as Zen, same as the first generation Ryzen products. But instead of being built on GlobalFoundries 14nm process, it's now built on GlobalFoundries 12nm process. And the difference between the two, well, that changes depending on whether you ask GlobalFoundries or AMD. But the generally accepted gains are 10% better performance and up to 15% better transistor density. The 10% better performance can be construed both in terms of frequency at a given voltage or a lower voltage at a given frequency. And the better density metric comes into the fact that GlobalFoundries has 7.5 track libraries for this process, as well as 9 track libraries and I believe 10.5 track libraries. So if you use the 7.5 track libraries, which basically means you're reducing your transistor size by having fewer fins in your transistor, then you can take the benefits of 50% better density. Now, what AMD has done is said, thank you very much, we'll have 10% better performance, but they have stuck with the 9 track libraries. So arguably there's not any better density, and we see this in the fact that AMD quotes the new parts as having the same transistor count and the same die size as the first generation parts. However, within that 12nm, speaking to GlobalFoundries, they have made improvements in the middle end of line and back end of line design rules. So there will be some size adjustment changes based on, fin height and maybe the density of, or maybe the thickness of some of the layers, which can be construed as, better density, which can be postulated to go forward into part of what makes it a better performing process than 14nm. But as far as AMD is concerned, it's practically the same, and they're having the extra performance. Thank you very much. So the news from AMD means that these parts can have up to an extra 200 megahertz over the first generation parts and run at a slightly lower voltage. This means that instead of the 4 gigahertz and 4.1 gigahertz overclocked parts we were getting on Ryzen first generation, we are now getting 4.3 gigahertz single core turbo on second generation, and AMD postulates that most chips should be able to do 4.2 gigahertz on all cores overclocked. So previously, where we had a sort of maximum bar based on the process for 24/7 running if you were slightly overclocking, now the new chips, because of the process, the bar is slightly raised and they go to meet that bar as well. So the 2700X, Ryzen 7 2700X, is the top part. It's been the highest, and that does hit the 4.3 gigahertz on single core. Now, the four CPUs are 2700X, 2700, 2600X, 2600. So they pretty much follow the exact same positions in the stack as they did for Ryzen first gen. It's almost like a instant replacement. What people have picked up on is that there is no Ryzen 7 1800X equivalent. There is no Ryzen 7 2800X. So when previously AMD had 3 processors in that Ryzen 7 segment, they've now moved down to 2. So the Ryzen 7 2700X, which occupies that top spot and replaces both the 1800X and the 1700X. The reason given from AMD is that 3 chips previously was a bit too crowded, so 2 chips services that market better. I would also argue that the 2700X is already quite at the limit of the process, so they're already getting the peak frequency out of those chips, on a reasonable scale, which makes it profitable for them.
I mean, have you done any overclocking of the new Ryzen chips?
So I managed to take a sample and get it to 4.35 gigahertz all core, though I didn't test necessarily. That was stable enough to run Cinebench and 3D Mark. I didn't test it for, ultimate stability.
Okay, so you haven't even been able to push another 100 megahertz on it.
No, but having the all of the cores up to about 4.2 definitely did seem doable.
Okay, so it just sounds like that AMD is very much at a frequency wall there for GlobalFoundries process.
Which is fine. It does mean 10% overclock is probably even 10%. I think on single core is going to be freakishly good. And
10% would need to get you up to 4.7, 4.8. So that is actually a lot of megahertz.
But the fact that they're not coming out with a 2800X because the 2700X is at that limit, I think is reasonable. Also, the fact that AMD have, at the beginning of the year at CES, said that there will be Threadripper processors, the high-end desktop processors, built on this, built on 12 nanometer, built on the second generation silicon designs later in the year. There are chances are that any chips that come out of the factory and are better performing than this 2700X might be saved for the Threadrippers later in the year. I've got nothing to corroborate that, but it would seem likely. Because they've always said that the top 5% of parts go into the Threadripper and the Epics. So
yeah, it makes a lot of sense. That's where your greatest profits are. You don't necessarily want to give your best chips out to go on cheap desktops. You want to save those for your best customers.
Pleases the shareholders as well. So one of the new features with the Ryzen 2000 series is in what AMD calls Precision Boost. This generation is called Precision Boost 2, and the way it is implemented on the systems is that it adjusts how Turbo reacts to loading. So for anybody that's familiar with how Turbo has worked in the past, what the system does is it determines how many cores are currently loaded with programs, and then based on how many cores are loaded, it will adjust the frequency of those cores to a predefined lookup table. So you could have one core at 4.2 gigahertz, 2 cores at 4.2 gigahertz. Then the minute you hear 3 cores loaded, or 3 threads loaded, you'll go down to 4 gigahertz, and then it will continually sort of drop off until it hits the all-core turbo. It's a very simple lookup table that is defined in the BIOS firmware, and motherboard manufacturers can adjust it as they see fit, which makes reviewing CPUs sometimes difficult. But for AMD, what AMD has done is they've enabled what's called Precision Boost 2. Now, instead of using a lookup table, it does a dynamic adjustment on the fly based on how much power is being drawn, what the thermals of the system are, how many threads are loaded, and possibly some other factors. But the idea is that you have this turbo which has a dynamic response. So instead of getting that step function where you drop down immediately when you hit three cores loaded, you now get a very sort of gentle curve that aims to use more power on the chip earlier in the loading. So you get a better turbo performance when you go beyond one core loaded. That's the idea. AMD can also adjust this in 25 megahertz increments. Their multiplier allows for 0.25x multipliers, so they can do 25 megahertz increments. And we tested this. We saw that in the key parts between sort of three threads loaded on 3 cores loaded, on the 2700X versus the 1800X. When you get sort of 3, 4, 5, 6, 7, 8, the chip would draw 20 watts more, which translated into better turbo frequency and better performance. So when AMD says, well, using these new processors, you get a 10% better overall performance, that's, slight changes in what they've done in the core, plus the extra frequency, plus the turbo response. So for any test, so our compression test that uses WinRAR, that is a variable threaded load. So that will see a better uptick than something like Cinebench, which just goes flat out. Our compile test uses variable threads, so that will have a better uplift than something that completely goes all out. So Precision Boost 2 is a better way to do turbo. Technically it was on the APUs, but now we're in a more thermally unlimited scenario where it matters more in performance. When the downside of this is it does draw more power. So anybody that's building a small form factor system that isn't too hung up on performance can actually disable it in the BIOS, so they get a lower power profile. But it's there, it works.
How is power consumption of the new chips overall? I know we have some higher TDPs here for the fastest parts.
So the top-end chip does increase the TDP by 10 watts. Now, TDP as a definition is arguably meant to be the base frequency at all cores, so comparing it against the turbo results, as people are used to doing in the past, is perhaps a little erroneous. So we are seeing a small power uplift, but it's in line with what AMD prints on the side of the box, which is, you don't necessarily want something abnormal to happen there. But we definitely get what we expect. But that's the only chip that has increased in TDP. The non-X chips are still 65 watts, and the Ryzen 5 2600X is still 95 watts. So there's parity there between the previous generation parts. Specifically on performance, so even though AMD hasn't done any design changes to the chip, anything in terms of the silicon layout, they have been able to adjust and tweak the firmware inside the chips, and as a result they've managed to reduce cache latency. So when a program comes in and it needs an instruction or it needs data, it checks the L1 caches to see if the data's there. If it's not, it reaches out to L2. If it's not, it reaches out to L3. If not, it reaches out to main memory. So any program that's waiting on data, the quicker you can get that data, the faster the program will run. And what AMD has managed to do is decrease the latency on their L1, L2, and L3 by at least one cycle. One cycle for the L1. With the L2, it's come down from 17 cycles down to 12, or down to 11 even, though there's a bit of issue there because AMD initially launched the Ryzen 1st gen with 17, then Threadripper came out with 12. So they were already making some tweaks there, but for the full generation to generation difference, it is a move from 17 to 11. The L3 cache also comes down in latency. And now it's the overall headline here is that AMD said 3% better IPC, 3% better instructions per clock, which doesn't seem a lot, though reducing the latency of an L1 cache is really difficult, because you've got to make sure that the data is all coherent and it's consistent. I mean, between the size of the L1 cache and the associativity and the latency, it's all got to balance up, and it's all got to be ultimately beneficial for the chip and the products in the end. So the fact that they're able to go away and say, well, we worked on this was low-hanging fruit, and we could implement it without a silicon design change is good. It won't be backported because there are different ways in order to implement it in how the CPUs are manufactured as well. So ultimately, the end is it's better for everybody because you have a lower latency caches, which leads to 3% better IPC. 3% is AMD's number. We got 3.1% on our tests, so that aligns pretty well with what we saw. And AMD ultimately said 10% better overall performance. That's IPC plus frequency plus turbo boost. And yeah, we pretty much see that. So AMD's being truthful when they say these things, and our job as journalists and analysts is to make sure that they're definitely keeping to what they promise. But overall, these chips are good. I mean, AMD's resurgence into high-performance x86 CPUs last year was great. It provided competition that the market needed, and as a result, with these chips, AMD is closing the gap in single-threaded performance. They're still a little way off, because Intel has kind of hammered that single-thread core design for several generations now, whereas this is AMD's Zen Plus, so 1.5 gens on their current core design, so there's still ways to go there. AMD is, for the same price Intel chip, AMD is ahead in most, if not all, multi-threaded scenarios, because you're comparing an 8-core chip versus a 6-core chip, both with multi-threading, so whatever AMD loses in single-core performance because you have more cores, and if the program is fully multi-threaded, then AMD wins those. AMD is still behind in a few things, so when it comes to AVX instructions, Intel has a big lead there. Intel is still regarded as much better in prefetching data out of caches and main memory. In Intel's core design and AMD's core design, they have what they call a micro-op cache, so if an instruction was recently done, they can look it up in a very quick cache to bring it in rather than actually decode it, which saves time and power. Intel's had that for several generations now. This is AMD's first generation, so Intel has a slight lead there. Intel's core is also, a little bit wider thanks to the vector instructions. So AMD's next generation chip, if they want IPC parity with Intel, they can't just go wider. AMD has to be clever here. So when AMD launched then, they were talking about their neural network branch predictor and zero cycle loop parts of the silicon. So AMD has to keep doing clever things to produce a core which is as competitive with Intel. However, we have seen issues regarding Spectre and Meltdown in some performance. Those affect Intel more than AMD. So while AMD is trying to reach for the bar, arguably that bar is coming a little bit lower as a result of those patches. More so on the server side, obviously, and the storage side. But
they just got to make sure they don't sort of fall into a trap there. They can win now for the moment, but once Intel fixes this in hardware, AMD still needs to be able to completely catch up to what Intel can do if they want to match them on the IPC front.
So the thing is, you say fix it in hardware. Now, fixing it in hardware might still have the same performance penalty as these kind of soft patches.
It depends on how they fix it. We'll take Spectre off the table for a moment because that's a whole crazy class in and of itself. But the Meltdown stuff, clearly you can do it without having a Meltdown vulnerability in hardware because AMD does not have a Meltdown vulnerability in hardware.
But again, it's as you say, it depends on how they fix it. If they fix it as the patches have already done, but they do it in hardware, then it's still going to have the same performance deficit. It's how can you patch it but still retain the high level performance you had pre-patch.
Yes, and I expect Intel will ultimately get there. We'll see what was it, Cascade Lake is due out later this year?
Something like that.
Yeah, so we'll see what Cascade Lake delivers, because that is on the list of things that's going to be hardware patched, and we'll see just what their short-term hardware fix is. And if it's not something extravagant, then I'd certainly expect Intel's long-term plans to contain a more extravagant fix.
We'll see. I mean, there's also another argument about 10 nanometer, which we won't have here.
What's 10 nanometer?
I don't know, ask Intel.
I did, they said 2019.
Oh, yes, that was one of the announcements, wasn't it, this week? Coming out of their financial analyst call.
Indeed, but that'll be a discussion for another time.
The next part of the podcast I want to bring up is something actually related to our Ryzen 2000 series testing. So we published our review. We managed to get all 4 chips for launch. It was kind of crazy annoying because I so limited time to test because I went away for Orthodox Easter weekend and the package with all the hardware arrived 15 minutes before I left for the airport. So all the hardware had to sit for 5 days untested until I got back. But when it did, I fired it up. I have automated scripts for our testing, so I can just push the button and off it goes, and then I can move on to another system, push a button, off it goes. For our testing, we implemented all the Spectre and Meltdown patches for all the systems we had. So we retested Intel's 8000 series Coffee Lake. We also did Skylake X. We also did Skylake and a Kaby Lake, just so we have multi-generational performance with the Spectre and Meltdown patches, also using Windows 10 RS3. With the Ryzen 2000 series, we also implemented the same patches, also the same OS, and we didn't have time at that point to run the first generation Ryzen on new chips. But the end results that came out, the CPU results were pretty much, exactly what we expected. AMD with the minor increase in performance compared to where Intel were. However, it was picked up very quickly after we posted the review, given that we were still writing the review as the embargo lifted, that our gaming results showed AMD ahead of Intel, whereas other publications showed that while AMD had improved, AMD was still behind Intel. Now, this was especially true at 1080p Full HD gaming. Our 4K results kind of lined up with other people's on most games. However, it was our 1080p results that, showed the biggest difference, especially with AMD ahead. Now, when you have a major shift in performance like that, lots of people like to add lots of commentary. So especially when you've got some websites saying one thing and some websites saying another. We initially put this down to the fact that we'd used our Spectre and Meltdown patches, and they seem to have had a more negative effect on the Intel system, which was kind of predicted, given how each system reacts to the vulnerabilities, but perhaps not to this degree. So as any professional would do in this situation, we decided to do an audit of our code. Now, I mentioned that I have an automated test suite. Among that, I run a series of commands relating to, disabling Windows Update, making sure I don't get pop-ups, making sure that Windows Defender doesn't come in and ruin a benchmark. As much as Windows 10 is now the standard, there are still plenty of Windows options that like to take CPU time away from you if you're not paying attention. Especially with the suite that we use, we have, consistent gaps between benchmarks, and if that gap is just slightly too long for an idle process to come in, and then if something goes wrong with that process, it can take CPU time. So we did an audit of our code, going through line by line of exactly what happened. And it turns out that the performance we were seeing on our test suite was due to how modern systems, and in particular modern x86 systems with Windows, implements timers. So a timer in a system ensures that the events on that system, are linear. You can have a record of exactly when each event occurred, and then you can follow the events and make sure everything occurs in order. The timers also have a secondary aspect, and that's to ensure that 1 second on the system is equal to 1 second in real life. If you've ever had, an old analog watch or clock that after a couple of weeks ends up being a few minutes slow, that means 1 second on that clock is not equal to 1 second in real life. So the timers on a modern system essentially do, for the most part, those two main things. They ensure a linear sequence of events, and they ensure that time on the system is coherent with reality. Now, a system can have many different timers in many different locations. People know that quartz crystals keep time. You can also have electrical circuits that keep time based on the frequency of the circuit. And for the most part, these systems and Windows will use a variety of timers for a variety of different things. So some timers that people have heard of are the TSC, the timestamp counter, the RTC, the real-time clock, or the HPET, the high precision event timer. Now, each of these timers runs at different frequencies, so they have different levels of accuracy. They also have different levels of latency. So if you reach out to a particular timer, it will take a while for the results to come back to say, well, actually it's this time. Also, the timers have different implementations. So some can be used as a countdown timer for an event occurring, or some will just continually count up. And in order to fire off an event at a particular time, you have to make sure you hit the clock at exactly the right time. So the way it used to work in single core systems is that the individual core on the chip would have a timestamp counter and a circuit on the core, and that was, you're only dealing with one core, so it's linear, and that's how it goes. Now, when multi-core chips came along, it still worked, but it wasn't always consistent. You could have a slight mismatch of clocks on different cores, which if you're trying to keep track of events is an issue. So most systems moved, especially with Windows 8 and Windows 10, implemented the high precision event timer, or HPET. And HPET was integrated into the chipset, and it was designed to save some money for embedded designers. So you didn't need like an external clock gen for synchronization, because this HPET had a series of minimum specifications that had to be adhered to, but overall you were designing a low-cost embedded system with one less component, so it was cheaper. So HPET requires a minimum frequency of 10 megahertz, and like I say, it's based on the chipset. The first systems that implemented HPET that we deal with run at around 14 megahertz. However, the latest Intel platforms, specifically X299 and all the Skylake-based platforms, have a HPET of 24 megahertz. Now, as I said, this HPET is more accurate, so it enables for the 1 second of system time to equal 1 second of real time, because of the accuracy. However, it is a high latency timer. It takes, I've read, I've not actually confirmed this myself, but I've read that it can take up to 1,000 CPU cycles to poll this timer. So if you're relying on that sort of 1,000 cycle granularity, you have to predict ahead when you need the timer. So one of the issues when HPET is not enabled, especially for extreme overclockers, is when the base frequency of the system changes. So the base frequency of most systems nowadays is 100 megahertz. If you are overclocking in the operating system and you move to 105 megahertz and you're still using the RTC on the system, the real-time clock on the system, you would end up with several % time drift. You'd have the situation where your watch ends up, several minutes fast per hour. Now, in extreme overclocking, two things are required, accurate result and accurate timekeeping. And the way that HPET was enabled on Windows 8 and Windows 10 meant that accurate timekeeping wasn't given. So in the overclocking world, what they enforced were a set of rules where this HPET, this timer, had to be forced on. In order to keep the real world and the system time accurate, by using the high resolution timer, ensured that consistency. Now, at the time, there wasn't necessarily a performance issue. The way it was implemented means that if you forced HPET on in the operating system, you wouldn't see much of a performance change, within maybe 1%, if anything. Back then, this was back in 2013, it was an issue for the extreme overclocking guys. So the way HPET is enabled is a bit odd. I'll cover this just briefly. So you have two switches, one in the BIOS and one in the OS. Now the one in the BIOS is a simple on or off. If it's off, then nothing in the system has access to the high precision event timer. If it's on, that means the switch the switch now moves to the operating system. Now in Windows 8 and Windows 10, that switch can be put into two positions: default or forced. If it's default, which is what happens when you normally install Windows, the system will say, okay, I have a bunch of timers at my disposal. I have a pool of timers, which include the real-time clock, the TSC, HPET, all these different timers. So I can use the one that I need at the right time based on the resolution I need and latency requirements. And the idea is that the operating system manages this automatically rather than the software. That's the OS in default mode. The OS, when you flip the switch, can turn it into forced mode, where it basically turns around and says, the only timer I have access to is HPET. The only timer I have access to is this extremely accurate, high-resolution timer. However, it does have high latency. Now, again, back when HPET was first introduced, back in 2013, there wasn't a performance difference in using HPET. However, from what we've done in testing, and verified by a few others, is that with X299, with Skylake and Skylake X, that has changed. Now enabling HPET or forcing HPET in the operating system, when it's enabled in the BIOS, does degrade performance. This is why when we did our Skylake X review, we didn't actually publish any graphics numbers at the time, because we came out and said our numbers don't look right. They're much lower than what we expect, and we're going to try and narrow down the issue. Now, at the time, we didn't find the issue. We definitely looked and retested, but for some reason, it never came to our knowledge that the fact that we were enabling HPET at the time, we never found out that was the issue at the time. We now know it's the issue now. Because the reason why we enabled it in the first place was because, well, overclockers use it for consistency. I'm, in a past life, an extreme overclocker. At the time, there was, arguably no performance difference, especially, for day-to-day workloads that we test. So it's perfectly fine to enable it and to make sure that we can keep 1 second in the real world equal to 1 second system equal to 1 second in the real world. The idea is we didn't want motherboard manufacturers to do some funky thing where we ended up being having the wrong benchmark scores, which then ended up being presented to the readers. That's ultimately why it was implemented. It was kind of a set and forget. But with our audit, we've turned around and said, well, actually, with Skylake and newer Intel systems, there is actually a performance deficit. We did so for our second set of testing when we tested with HPET on and off, or default and forced in the OS. We saw not much difference in the CPU tests, to be honest. But in our GPU tests, we did see results that were, affected around 10% on AMD at full HD, but with Intel, it was more like 40 to 50, and in a couple of cases more at 1080p. Now, you don't want a drop of 40 to 50% in your 1080p gaming at any rate, and this is essentially what HPET was doing. Now, why is this important? Because if if a standard install with Windows doesn't force HPET, then why does it matter that much to most users, except for extreme overclockers? Well, the fact is that some software will force HPET on and won't change it back if you disable the software or uninstall it. So this is mainly some monitoring software and overclocking software. They will load up for the first time and say, hey, we need to make some changes for your system. Please reboot, because in order to change HPET from default to forced or vice versa, the system needs to restart. Some of that software, so for example, Ryzen Master on AMD, will actually enable HPET because it enables their monitoring to be better because they're using the higher precision timer. So users who install this software are going to ultimately see a potential performance deficit when they game at 1080p. In 4K gaming, we didn't see much of a difference. A couple of games were, 10% maybe on the Intel side, but on AMD we saw next to no difference. So back at the beginning I said, with single core we used TSC, timestamp counter. Now in modern CPUs they have what's called an invariant timestamp counter, which is slightly different. You have a CPU instruction called RDTSC, which helps keep the time synchronized. You can still get clock drift using this timer. However, it's not on the scale of what could happen. It's still important for extreme overclockers, but not for common users. So, for example, with some of our timing software, we saw a 0.01 second drift in 2.5 minutes, which equates to about 6 seconds per day drift. Now, our biggest benchmarks run for a couple of hours. So yeah, we might end up seeing half a second drift in a couple of hours. So ultimately we can still we don't need to force this high precision event timer in order to make all of our benchmark numbers work. So with this instruction, which can be used as a system or a kernel call, we're now retesting all of our Ryzen 2000 series review samples and updating that review with the new data, which is more in line with what everybody else gets, plus the Spectrum meltdown patches that we implemented, showing that AMD and Intel very competitive at 4K with 1080p. Intel is still ahead in most cases, by anywhere from a few percent to 10%. So we're going to retest those, but ultimately we're actually coming to a point where we're going to implement our 2018 test suite. So we're not going to focus too much on the older data because we're going to accelerate and move straight into our 2018 test suite. So we're making sure that every system we test has the Spectrum meltdown patches enabled. We've got Windows RS3 with all the patches required. We've got new GPU drivers, new tests, new gaming tests, more modern games, to make sure that they're more relevant. So our focus going forward, once we do this recap of testing, is going to be on that 2018 test suite. Now the roundup of all this is this issue affects Intel more than AMD. Not entirely sure why. We think it's because the high precision event timer on the more modern Intel systems run at 24 megahertz, whereas previously, when it didn't affect the system as much, and on AMD, they're at only 14 megahertz, 14.32 megahertz or thereabouts. So it could be that the extra precision is causing additional latency issues. But the second part is, our CPU tests weren't really affected, but our GPU tests were, especially at the lower resolutions. Now, this comes down to how GPUs use the timers versus how a CPU program might use the timers. So in a game engine, the developer usually has lots of hooks in the game to poll the timers. They need to know exactly how long it's taking to process the lighting or the Z buffer or anything like that, to make sure that the quality of the game is consistent. Now, with modern games, they will automatically adjust the resolution based on your frame rate. If you say, I want a target of 60 frames per second, they will either super sample if you're beyond that, or reduce the resolution dynamically in the game if you're not hitting 60 frames a second. So that all involves timers. You need to make sure that your frames and all the data for those frames are moving through at the right speed and at the right time, and everything gets in place at the right time and computes within the reasonable amount of time. So you're polling the timers all the time. Now, if you have a high latency timer, like the high precision event timer, it's going to affect it a lot more. Now, with a CPU test, if you're just doing a straightforward, say, video transcode, you don't need a timer. You just need to make sure that everything's necessarily in order. But for a GPU, you need to make sure those timers are accurate. And if you've got a high latency timer, then that can reduce your frame rate. I'm speaking GPUs now, Ryan. Would you like anything to add?
Not too much. You sort of hit all the high points there about the high performance event timer. I suppose the one bit of good news is these days the games tend to be much more GPU limited than they are CPU limited. So the real world implications of this are quite limited, but still, it was an interesting find to say the least, and does mean that we have to go about things a bit differently. But the end result is that order has been restored in the universe, and it means AMD has a little more incentive to work just a little bit harder to catch up to Intel for the next generation.
It's, as a result of our review and then our timer testing, it was interesting to see how many people came out to us and say, well, I play esports and the only thing that I matter about is frame rate. So I don't care necessarily about the resolution or the quality. All I want is that frame rate. They run at 720p at low settings just to make sure they have 240 FPS. It's those people who would be hit hardest by this.
Yes, very much so. Anywhere where you're going to get high CPU frame rates, or at least where you should be getting high CPU frame rates.
It does make how I'm choosing my 2018 test suite for gaming interesting, about what resolutions I should pick and what quality and how they're going to affect the CPU. Next on our list of topics is news about Kaby Lake G. News about Intel's Core with Radeon RX Vega graphics. Now, if you've not heard about this chip or you've only heard about it in passing, this is a revelation that kind of shook the industry at the beginning of the year, end of last year. Here was Intel designing a chip, or designing a package that had both Intel Core silicon on it, technically a H series 45 watt processor, connected to an AMD graphics package, which then through Intel's embedded multi-die interconnect, embedded multi-die interconnect bridge, was connected to high bandwidth to memory, HBM2 memory. What the big news about this was the fact that AMD was selling chips to Intel because Intel wanted a part with better graphics in that price point. Either they had a customer that required that sort of part in that price range, or they said, we want to tackle this. We want a part that goes into products to, essentially take some of the low-end graphics space. In that agreement, in that product, it's purely an Intel product. So only Intel are selling it. Only all the drivers are labeled Intel. All AMD is doing through their semi-custom division is selling Intel a chip. They just give Intel a tray or a roll of chips and say, there you go, up to you to do what you want. So it's up to Intel to bin them for performance, to decide how many compute units, what the frequencies are. Obviously, they can go back to AMD and say, well, what do you suggest based on what your manufacturing is doing? Standard supplier agreement. But this was a purely Intel project. It's a purely Intel product called Intel Core with Radeon RX Vega M graphics. Now, apparently, one word in that name is perhaps erroneous.
Yes, and that would be the Vega part. And this is another one of those interesting little stories that came out after the product launch. So credit here to Gordon over at PC World for initially spotting this. if you run GPU-Z or various other tools that report the DirectX feature level on a GPU, notice that it was reporting feature level 12.0. Feature level 12.0 is a slightly older feature level set, notably that it's not the feature level set found on a proper Vega discrete GPU. The Vega 56 and 64 cards that were launched back in August, and then the Vega APUs that were launched at the end of last year, both support feature level 12.1. This is currently the newest iteration of the DirectX feature set level. And so the fact that the supposedly Vega GPU was reporting 12.0 was more than a little odd. And a little more digging, again, turned up more and more proof that features that you would expect on a Vega GPU were missing. Various other sub-features were not available, certain OpenCL features were not available, etc. So everything was pointing to sort of one of two possibilities. Either that this wasn't a complete and true Vega GPU, or for some reason that AMD's drivers were only enabling sort of a baseline level of features here, as opposed to everything that Vega was capable of. However, late last week, AMD engineers turned in the code needed for the AMD GPU driver code to run this new GPU, and essentially all the relevant code was checked in under the Polaris branch. So Polaris graphics core next for AMD's 2016 GPU architecture. So all the code changes that were made on this driver to enable it, that were architecture specific, were all made under there, all but confirming that the actual compute and graphics core of the chip is actually. And this is where we sort of get into an interesting discussion about whether this makes the Vega M a true Vega part or a Polaris part with better memory. The memory controller side of things definitely seems to be lifted from Vega. Vega, of course, was AMD's first product that supported HBM2 memory, and this Vega M also supports HBM2 memory. AMD's semi-custom operations means that they can sort of mix and match different parts of a GPU. You know, use a display controller at one level, use a compute core at another level, use a memory controller at a third level, etc. So it looks like what AMD has essentially done for Intel is to take take Polaris and then swap out Polaris's GDDR5 memory controller for Vega's newer HBM2 memory controller. But, and this is critical, that appears to be it. Every other aspect of this chip appears to be Polaris. And so you raise the question, is this really a Vega? And no, it really probably isn't. And I won't berate Intel too much here. They aren't going to change how they advertise it based on a podcast, but this is not a situation where we would have agreed had we known in advance that this was not a head-to-tail Vega GPU.
So, I mean, with regard to this naming, we have seen Intel's philosophy on naming change over the last couple of years. We're currently seeing 8th generation core products being built on with a number of different microarchitectures. Intel's now, when you said 4th gen, you knew which architecture it was. With 8th gen, you don't know unless you actually look into the part number and into the part specifications. The reason being is Intel is saying, well, you know, our latest is 8th gen and we're going to be fluid in what products work for which market. So an Intel argument here could be, well, Vega is the latest and we're using a Vega memory controller, because if we called it Polaris, people would say that's old technology.
Yes, and unfortunately people would be right. And not to knock Polaris too much here. It doesn't. These findings don't change anything about performance about this new Kaby G Vega M part. It's still really fast for a chip of it. You've essentially integrated a mid-range Polaris GPU onto a package along with an Intel CPU and given it plenty of memory bandwidth. So all the performance aspects that we've seen so far from our review of Hades Canyon and whatnot, it's still a really fast chip. It just means that the GPU is somewhat dated from a feature perspective. And this really has all the hallmarks of essentially a project that had to be brought together under an accelerated timeline. This probably wasn't something in 4 years ago, 3 years ago, to semi-custom something. So the impact of it being Polaris-based as opposed to Vega-based is going to be fairly limited. It certainly isn't going to affect game compatibility or anything. It means the DirectX 12.1 feature set isn't going to be available. It has some impacts on ROP performance because under the Polaris graphics architecture, ROPs aren't an L2 client. And Vega's sort of marquee feature, rapid packed math, is not going to be available here. So games such as Wolfenstein and a couple others so far that implement support for it don't get that extra push in performance on Vega M. A little more broadly speaking, it's just somewhat unfortunate because Polaris itself was an extremely minor revision to AMD's earlier graphics core Next 3 ISA, and that was originally released in 2014 for the GPU that went into the Radeon R9 285, that GPU being Tonga. So we're essentially looking here at a 14-nanometer version of a GPU architecture that was first released in 2014, so it is a few years old here. The irony being that because of that, it actually is less feature packed, supports less features than Intel's own integrated GPU. The integrated GPU on Kaby Lake G, is feature level 12.1 capable, and as Ganesh picked up in his Hades Canyon review, the integrated GPU is capable of supporting VP9 video decode, whereas the AMD on-package Vega M GPU does. So that means that there is no hardware acceleration of video decoding on YouTube. Again, small potatoes, but just weird things here that come from using an older GPU architecture. Which is not to say that it's all bad. Importantly, Polaris supports native HDMI 2.0, something Intel doesn't. So for Hades Canyon, the Dell XPS 2-in-1, etc., you can have proper 4K 60Hz HDMI output to televisions and whatnot with this chip, which is something that Kaby Lake on its own could not pull off.
What generation of GPUs does Apple currently use on its high-end systems?
It depends if we're talking laptops or desktops here.
Either.
Alright, so the Apple situation is very weird. If we ignore the Mac Pro for a second, because that thing hasn't been updated in years, Apple uses all of its laptops that have a discrete-inch MacBook Pro. But if you go into the iMac, the newly released iMac Pro contains a tried and true Vega GPU.
Okay, so it's not a case of a potential customer for this chip having a lot of Polaris-based software.
You could potentially argue that, but I doubt any specific customer custom side couldn't afford to implement something quite as new as Vega.
Speaking with AMD and Intel on this, neither will comment on if this is a multi-chip deal, as in if there'll be a next generation beyond what we currently have. One would assume that if there were a next generation, it would have Vega in it, and you'd get the uplift that provides. However, neither of them are saying that neither of them are saying if there will be a second generation. I think they're going to see how well this pans out first.
Would be very surprised if we didn't see a second generation without going too far off track here. It's going to be a few years until Intel can come up with their own solution that offers this level of performance. So I'd certainly expect to see more, but there's really sort of zero tells coming out of Intel and AMD about this one. But overall, it's just this odd little story about Vega. The Vega launch itself has been just sort of odd for AMD. Vega, of course, is sort of the rock star of the cryptocurrency world, so AMD can sell Vega GPUs day and night just to cryptocurrency miners. Vega is now at the core of their APU launches, but there's still some driver kinks to work out there, so the APUs don't necessarily get access to the latest drivers. And now you have Vega that's not a Vega in Kaby Lake G.
Well, it's kind of interesting how, you know, the Intel and AMD agreement, or, you know, chip sale occurs, because very soon after this product came out, changes were made afoot into Intel's strategy. Now, we've already covered Raja Koduri transitioning from AMD to Intel earlier in the year. However, Intel made a surprise hire. It was a surprise to me anyway. I'm not sure.
Yeah, I wasn't necessarily expecting this hire, but at the same time, I'm not surprised by the outcome. We are, of course, referring to Jim Keller, who Intel picked up, in fact, starting just yesterday now, to work for the company. So Jim Keller is a name that longtime AnandTech readers may be familiar with. He is essentially one of the rockstar engineers. He has worked for AMD, Apple, AMD again, Tesla, and now Intel. His major products include AMD's K8, Apple's early A4 and A5 SoCs, AMD's Zen CPU architecture, working on low power computing for Tesla, and now he is doing some new things at Intel. So essentially his specialty here in the last decade has been low power, high efficiency.
And a lot of companies would pay a lot of money for experts in that.
It is. Jim Keller can essentially write his own check here. He just jumps from company to company, working on whatever seems to interest him.
So he's been put in charge of Intel's Silicon Engineering Group, which kind of sounds like manufacturing, but isn't.
Yeah, it's a bit weird, and we really don't have a good definition from Intel on just what the Silicon Engineering Group entails. Certainly manufacturing is a part of it. It doesn't matter how good your architecture is. If your manufacturing sucks, or conversely, if you don't have good integration between your architecture design and your manufacturing capabilities. So I'm sure there's some low-level optimization work involved there, but it's not clear if Jim Keller is going to be the actual architectural side, or if he's just going to help Intel essentially implement these architectures in a low-power friendly way.
Well, so Raj Kaduri is heading up the Core and Visual group, which, and technically all the CPU and the GPU designs all come from that group, whereas the Silicon Engineering Group is more focused on, say, the SoC market. So they're not necessarily dealing with cores in the same way that the Raja's group will be doing. There might be some synergy between the two groups depending on projects. Again, it comes back to what you say, we don't necessarily have good insight into what he's doing. As it states, exciting initiatives to fundamentally change the way we build the silicon as we enter the world of heterogeneous process and architectures. So, I mean, this is even different from Intel Labs. So Intel's Labs group is, sort of cutting edge manufacturing, 5, 7, 10 years out, the sort of, moonshot type stuff. So this fits somewhere in between what Raja's doing and what Intel Labs doing. Again, it's ill-defined from our perspective, but
it is. It's one of those things where Jim Keller's going to work on this for a few years, and then Intel will come out with this amazing announcement, and then we'll go, "Oh, that's what he was working on. Cool."
Just like he did with AMD and Apple and AMD before.
Well, the Apple stuff was very secret. The AMD stuff less so. When AMD brought back Zen, that was...
Well, so, I mean, for some of these projects, like I say, he is a rock star. But, teams that build chips are 100 strong. He is just one person, and what he did at AMD was ultimately to take the team, make changes to the team as necessary, and put the team on the right track. Right.
Exactly.
He's not the one fiddling around with trying to make the L2 cache work.
Yeah, Intel has plenty of capable engineers. I mean, clearly they could always use some more, but Keller's hire seems to be more about project leadership and applying his expertise in certain fields than it is about making architectural changes at this point. The size of these teams has ballooned over the past couple of decades. When Keller started at AMD back in the 90s, the K7 team that he worked on was relatively small. Now even the Zen team vastly overshadows that, and Intel's design teams overshadow that even more. So whenever we have an announcement like this, we don't don't want to make it sound like Intel doesn't have many people working hard on these things, and conversely change the tide on his own, but with the right leadership can certainly have an impact on them. So we'll have to see just what Intel does with Keller, both in terms of his role and his projects.
But it's like what we said when Intel hired Raja, or when Jim was snapped up by AMD before. It's going to be a few years before we see any products which have the hand of these rock stars touch them. So
yeah, full start to end chip design these days, you're looking at 4 or 5 years, depending on just what Keller's doing. He may be doing, say, something close to optimization work, which may mean, you're looking at something out in 3 years, but still, it's going to be sometime in the next decade before we see the fruits of it.
And hopefully by then we might be on 7 nanometer, maybe.
Got to get past 10 nanometer first.
So, Intel hasn't just hired Jim Keller. We got word in the past week that Raja's right-hand marketing man from AMD, a long-time AMDer, Chris Hook, has also joined Intel. Chris Hook was with AMD for 17 years?
Yes, he goes all the way back to I think the very late 90s for what was then ATI.
So, I mean, the hand of Chris Hook is... I know him best through the events that he has held with AMD, because they're a little esoteric, such as going to Hawaii, or when AMD was sponsoring Formula One, there was the Abu Dhabi event. I think he had his hand in that as well. Or Polaris launch at Macau. So Intel have an interesting hire there. I wonder what's going to happen to Intel events in the future.
We'll see. Intel's a much larger organization overall, and relative to AMD, they actually have a market budget. So whereas Chris Hook's modus operandi here for most of the last decade, AMD has been guerrilla marketing, often out of necessity. With Intel, they can more traditional marketing. At the same time, it remains to be seen just what marketing projects he works on. Given his history with Raja Koduri, I have to assume that he's there to help Raja market his forthcoming GPU products. So, very familiar territory for Chris Hook. But there may be more to it than that, so we'll see.
It'd be interesting to see who else makes the jump, if anybody else does. Last on our list of news for this past week or so is... just a little tidbit that came out as a result of one of our reviewers, Tracy. One of his roles is that he reviews our power supplies because he has the very expensive equipment in order to do so. Plus, he's really, really good at it. And
really, really good is an understatement.
He was sent Corsair's latest power supply. Now, back at CES, we saw Corsair show in their suite a 1600 watt digital power supply. So the Corsair AX 1600i power supply. Now, AX is Corsair's high-end range. 1600 watts is overkill for pretty much everything except cryptocurrency. So it's vastly oversized for practically everyone. What made this power supply different than, say, the 1500 watt AX 1500i that they have, or the 1200 watt or the 1000 watts, is the fact that they were using new features new components inside the power supply that have necessarily been used elsewhere, but not in consumer products. Go on.
Gallium nitride MOSFETs, or just GaNs for short. So These are relatively new means of making transistors. Have been in other products before. I have to assume the military, for example, has been on this one for a little bit, but until now, cost has never been a pro into consumer products, even super expensive consumer products like kilowatt power supply. But here we are, finally, they're starting to show up in product. Even in this very first product, of course, reaping the benefits of it. So what makes gallium nitride MOSFET special is that gallium nitride, as opposed to silicon, has an incredibly high efficiency, especially once we're talking underload, where power is being sent through, and as leakage is inevitable. In a power supply, I mean, this is pretty much a one-to-one relationship here. So all the power that gets wasted immediately gets turned into heat and needs to be cooled by this power supply. And so even just losing a few percent of your power, could potentially be upwards of 100 watts of heat. So not a small matter.
So in the power supply world, we deal with what's called 80 plus certification, and it goes bronze, silver, gold. I think it goes platinum, titanium. So the more efficient the power supply at predefined load points, I think it's 20%, 50%, and 90%, or 100%. You can go to the 80 plus certification board and say, our power supply is this efficient. Can you verify and give us the certification? So if you want the best, you go for 80 plus gold, platinum, titanium, and you tend to pay for that benefit. Though the top end range, you're looking at losses of anywhere from about 6 to 8%. What the gallium nitride MOSFETs do is reduce that conversion loss to 4%, which
not even 4%. It was less than 4% at a 50% load, so about 800 watts. So that's always been the sweet spot for power supplies, and the change in transistors has changed that. But it's over 96% energy efficiency. At this point, you're losing very little power to actual transistors.
So you're using the more expensive component, which arguably means you can perhaps scale back the cooling because you don't need as much cooling, or in the case of most modern power supplies, you don't need to turn on the fan until much, much later, so you're reducing the noise of the power supply in the system. Now, these new MOSFETs are expensive, and this is Corsair's high-end product, so they're not going to skimp out on anything like that right now.
Well, no, I mean, actually, they have done both those things in a roundabout way. This power supply is actually, Tracy says it's closer to about an 800 watt power supply in terms of size, which means it's not some little box, but it's also not massive because it doesn't need so much cooling or regulation. And the fan does actually get to stay off fairly often because it's so cool.
So I own a Hercules 1600 watt power supply from Roseville. They used to do them, 4, 5, 6 years ago. And yeah, that thing is it's more than a brick. It's 2 bricks. It's massive. It's heavy. Obviously, because it's 1600 watts, it has, as many modular cables as you like. So having something which is, significantly smaller. If you need the power, it's there. Though the main takeaway from this is, as the first consumer product with these new MOSFETs, you can immediately see, because the power supply market is very competitive, other people are going to start using them. And if more people use them, cost comes down. If cost comes down, they go into lower rated power supplies. Going to lower rated power supplies, they become more efficient, and maybe the components become cheaper, and the cycle repeats.
Yeah, we're going to go through a sort of a traditional economies of scale process here. It's way too early to say if these MOSFETs are going to end up in every power supply in 10, 20 years or whatever. But certainly the future of the high-end power supply market, of the AX series, of the Seasonic titaniums, etc., is going to be that everyone is to want to switch to gallium nitride MOSFETs in order to increase their power efficiency, or really at this point to further decrease their power switching losses to reach these sub 4% levels.
I think a good bar will be when we see them in the sort of 600 watt silent power supplies, because we might end up seeing 700 watt or 800 watt silent power supplies with that level of efficiency.
It is, and with that level of efficiency, you really can push the silence part.
Yep.
So yeah, I'm looking forward to it. Power supplies are not a stagnant industry by any means, but we've been able to high wattage, high amounts of power for a long time now. So the change here is making the product not bigger, but making
it'll be interesting to see who comes out next with a similar device. So
I can't imagine they'll be too far away, especially the nature of these OEM-based designs.
Also, we have Computex around the corner. Computex at the beginning of June, my major show of the year. All the PC component manufacturers are going to be there. They will be showing off their wares. This year, Computex not associated with a major CPU launch, as far as I'm aware. If I'm going to get a call in a few weeks to say you've got 3 days to test something, I'll be mightily surprised and annoyed. But this show looks it's going to be full of iterative updates. Power supplies might be one. There's going to be a few announcements. I'm already getting invites through. I'm already getting press event invites through. We're going to see more systems using 8th generation Intel Core products. We might see a few more Ryzen APU systems. All the ones that we saw back at CES might now actually be ready to retail. So they'll be on the show floor. That's my immediate horizon. Planning for Computex. You've got WWDC.
Yeah, WWDC, Apple's Worldwide Developers Conference, actually takes place at the same time as Computex this year. Kicks off during the later days of Computex, as opposed to past years, where it's always been the week after Computex. As a result, even if Computex is a bit more on this side of the Pacific, Apple will have plenty of interesting things.
That week it's just going to be news.
And maybe a few surprise reviews. We'll see.
I know we've got some interesting reviews coming up. So yeah, thank you, Ryan, for joining me on the podcast.
No problem. Thank you, as always, for hosting these, Ian.
And thank you, everybody, for listening. More interesting stuff coming up ahead. Stay tuned, and we'll let you all know. So thanks for listening.